In this lecture, we are going to study about Schrodinger's time-independent wave equation, which is lecture 7 of Unit 1, Quantum Mechanics. Now, to recollect back what we have studied, de Broglie hypothesis states that matter particles also behave like waves. And it was Davison and Germer experiment which gave evidence that matter particles behave like waves. Now, Schrodinger describes the wave nature of a particle in mathematical form, and it is known as Schrodinger's wave equation. Consider a plane wave moving along the positive x direction with a velocity v. The equation of the wave is written as y is equal to a sine 2 pi by lambda into x minus vt, where a is the amplitude of the wave, y the displacement of wave in y direction, and x displacement along x-axis at any instant of time t. Taking the first and second order derivative with respect to x on both the sides, we get dy by dx is equal to a cos 2 pi by lambda into x minus vt into 2 pi by lambda. Taking the second derivative, you get d square y by dx square is equal to minus a 2 pi by lambda the whole square sine 2 pi by lambda x minus vt. We shall use y in the above equation. What is the value of y? As we have seen, y is equal to a sine 2 pi by lambda into x minus vt. When you substitute this y in this equation, what do you get? D square y by dx square is equal to minus of 2 pi by lambda the whole square into y. Getting the terms to the left hand side, we get d square y by dx square plus 2 pi by lambda the whole square into y is equal to 0. Now, in a complex wave, the displacement y is replaced by the wave function psi, and the wavelength lambda is replaced by de Broglie wavelength. What is the de Broglie wavelength? Lambda is equal to h by mv. Okay. And what is the differential equation we have now? D square y. Instead of y, we are writing it as the wave function psi. So get it as d square psi by dx square plus 2 pi by lambda the whole square. It was y. Now y became equal to psi is equal to 0. The equation that you see is d square psi by dx square plus 2 pi by lambda the whole square into psi is equal to 0. Now in this equation, we shall substitute the value of lambda. What is the value of lambda? Lambda is equal to h by mv. Now what does this equation become? D square psi by dx square plus, we are opening up the square, it becomes 4 pi square by lambda square. So lambda square is what? H square by m square v square. So finally, what is the expression we get? D square psi by dx square plus 4 pi square m square v square by h square psi is equal to 0. Now let us assume the particle is moving. So for a moving particle, the total energy is E is equal to U plus V, where V is the potential energy and U is the kinetic energy. So if you write the kinetic energy U is equal to E minus V. We know that the general expression for kinetic energy is what? U is equal to half mv square. Multiply both the sides with m. Then what do you arrive at? 2 into m into u is equal to m square into v square. But we already know u is equal to E minus v. Substitute this value of u in the above expression. So what do you get? 2m. Instead of u, you are writing it as E minus v is equal to m square v square. We have arrived at an expression for m square v square. If you look at the Schrodinger's equation, we have m square v square in the expression. What is the original expression? D square psi by dx square plus 4 pi square into m square v square by h square psi is equal to 0. So in this expression, substitute the value of m square v square. When you substitute, what do you get? D square psi by dx square plus 4 pi square. So instead of m square v square, we are writing it as 2m e minus v by h square into psi is equal to 0. Multiplying 4 into 2, what do you get? D square psi by dx square plus 8 pi square m by h square e minus v into psi is equal to 0. This expression is the one-dimensional Schrodinger's equation. Okay, where we know that E is the total energy and V is the potential energy. So in different cases, we can substitute what is this potential under which the electron will move. So in this lecture, what did we study? We studied what is Schrodinger's one-dimensional wave equation.